Welcome back my dear friends, a very good morning, good afternoon, good evening to all of you, and this is the TQM2 lecture on the NPTEL MOOC series, and we are in the 37th lecture. That means we are in the second day of the second class for the last week, and I am Raghunandan Sengupta from the IME department, IIT Kanpur. So, if you remember, in the last class we did not cover much of the slides, but there were a lot of discussions which are basically given, and hope it is clear to all of you. So, we were discussing the multiple linear regression and did mention in very few words why multiple linear regression means the linear part of the betas and not the non-linear part of the betas, because we are going to partially differentiate the sum of the square of the errors with respect to the unknown parameters with the betas, put them to 0, find out using the normalized linear equations, find out the betas, use these betas to estimate the values of y for the nth plus 2, nth plus 3, nth plus 4 reading, then find out the difference of the using these errors. Errors means the difference between the y actual value and the predicted value, and we are using the values of beta hats, whatever that is, beta naught, beta 1, beta 2 till beta k. So, those hats we utilize to predict the values of y, which are the y hat values, find out the difference between the actual y and the y hats, the predicted values of y hats, find out the errors, sum of the errors. In the long run should be 0, because the expected value of the errors is 0, the variance should be 1 or sigma square as the case may be, and then we proceed. And then we found out, and we did discuss that how we can find out the betas using the simple concept of matrix notation, how we can find out the sum of the squares, how we can find out the sigma square. And at the fag end of the class of the 36th lecture, I did mention that a concept of degrees of freedom, that means you are losing set of informations. So, if there are 2 betas, you basically use those set of observations to find out beta naught, beta 1. If you have 3 betas, you basically use them for 3 times to find out beta naught, beta 1, beta 2. Hence, you are losing the degrees of freedom. Hence, the sum of the squares, whatever the formulas which you use, main part of the discussion was basically you are going to divide by n minus p. P was basically k plus 1, where k plus 1 is the number of betas you are going to estimate. So, you are losing informations, hence the degrees of freedom would be n minus p, or n minus in the bracket k plus 1, and n is the set of observations. The method of the least square produces an unbiased estimate. I did mention the word unbiased estimate in the 36th lecture. So, produces an unbiased estimate of the parameter beta in the linear regression. So, what we mean by unbiased estimation is the expected values of the beta hats in the long run should be exactly equal to the values of betas, which is the example. 2 very simple examples which I gave was, keep tossing a coin, number of heads for each such set of tosses which you have. If you have say for example 200 tosses, find out the chances of heads in the first 200, then chances of head on the second 200, third 200, so on and so forth, add them up, divide the number of 200 such tosses you have done, find out the average of the average, you should exactly be equal to 0.5. So, it actually means the unbiasedness. So, by unbiasedness we mean that the expected value of beta hat should be equal to beta. Now, the variance property of beta is expressed as the covariance matrix. So, if you basically have the, so betas are what in the vector notation, the first term would be beta naught, beta 1, beta 2 till the last term is beta k. So, obviously, there would be a covariance between them. So, if you want to find out the covariances and use simple algebra matrix notation, the covariance structure would be like this. You have sigma square, which you have already found out. Now, here the term which we have, so if you have what was basically x prime. So, if you know, let us come to x. Basically, x was n cross k plus 1 and x prime was k plus 1 cross n. So, x prime cross x, if you multiply them, you will basically have k plus 1 cross k plus 1. Transpose of the inverse of that will also be k plus 1 into k plus 1. So, when you find multiply sigma square is a scalar. So, obviously, the actual matrix of the covariance of beta is basically a matrix of k plus 1 k plus 1. So, which should be right, because as we have been discussing. So, what we have, the covariance of betas, the primary or the principal diagonal would basically the covariance of beta naught with beta naught itself, which is the first element here. The second element cross along the principal diagonal would be the covariance of beta 1 with respect to beta 1, which is basically the variance of beta 1. The third element along the principal diagonal would be the covariance of beta 2 with respect to beta 2, which is the variance of beta 2, and the last element which you call along the principal diagonal, which is the k plus 1 comma k plus 1 cell number, would be the covariance of kth beta with respect to of itself, which is the variance of beta k, and the off the diagonal element with the covariances. So, the element 1 comma 2 and 2 comma 1 would be mirror image, which would be the covariance of beta naught with respect to beta 1 in the element 1 comma 2, and in the element 2 comma 1 it will basically be the covariance of beta 1 with respect to beta naught. So, obviously, they are a mirror image. So, this will give us the covariances. So, if sigma square in the equations, as we have just discussed that in the end of the 35th lecture, is replaced with the estimated values of sigma square, we obtain an estimate of the covariance matrix of beta naught, beta hat. The square root of the main diagonal element of the matrix, as I just mentioned few seconds back, it is the standard errors of the model parameters, or the standard errors, which basically standard errors is the word which we are using the first time, but it basically means the standard deviation of the sample. So, when we are talking about the standard deviation, we are talking about the population. When we are talking about the standard error, is basically the standard deviation of the sample, and we are talking of the variances, it will basically be the variance of the population, and when we are talking about the variance with the word sample variance, it would basically be the corresponding to the sample. So, the principal diagonal, if it is the covariance variance matrix, and we have found the square root. So, the principal diagonals with the standard errors of beta naught, beta 1, beta 2 till the last element, and the off the diagonal element would basically be the covariances of the beta I and beta j, where I and j basically change from 0 to k. So, let us consider the example 16 observations on the viscosity of the polymer. So, what is the y value is the viscosity of the polymer which you want to estimate or forecast, and two process variables are being utilized, which is x1 is the temperature and x2 is the feed rate of the catalyst. So, these are the parameters based on which we will try to find out the viscosity of the polymer. The equation which we want to basically estimate is the multilinear regression of the form y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon, where y, I am again repeating, is the viscosity of the polymer, x1 is basically the reaction temperature, and x2 is the feed rate of the catalyst. So, the observations are given 1 to 16, the temperatures are given, which is x1 in degrees centigrade from starting from 80 to 87, the catalyst feed, which is given in the rates of pound per hour, is from 8 to 12. So, I am just reading the first value and the last value. So, there are 16 readings, and the viscosity values, which is the y values, are given from values from 2256 to 2328. So, this is the viscosity data for the example, and the viscosity is given in Stokes. So, this is the in centi-Stokes, which is Stokes into 10 to the power minus 3. And when we have this, so the matrix R, if you remember the matrix X, because there is beta naught. So, the first column would be the 1 ones. So, how many ones? They would be 20 observations. So, and the observations on the second column would be basically corresponding to x1, observations in the third column would be corresponding to the x2, and the y's are the centi-Stokes values of the viscosity starting from, as I mentioned, 2256, which is the first value, which is y1, till y20, which is 2328. So, once we have that, we can find out very simply in the X matrix, then you can find out the X transpose matrix, because transpose would be rows would be columns, columns would be rows. Once we find that, so X cross X matrix is given, and then we find out the x. So the if you check it, the size is 3 cross 3. Why 3 cross 3? Because beta naught, beta 1, beta 2, and x transpose into y, the value is given. So again the size would be 3 cross 1 as we have been mentioning. So once we find it, then put them in this equation. What was the equation? Equation was basically x into x prime, x prime into x, that multiplied, find its transpose, multiplied by x prime, multiplied by y. In the sequence you will find out the 3 cross 1 values which is corresponding to beta hat. So that beta hat comes out to be this, which means beta naught is equal to, I won't read the decimals, it will be 1566 is the value of beta naught, 7.6. Let me bring the decimal values for beta 1. So it will be 7.6 for beta 1, which means that for the change of the temperature, the rate of change of the viscosity for that polymer in centistrokes would be of the unit of 7.6. So 1 unit change in the degree centigrade temperature would increase or decrease the value of the viscosity level by 7.6. Similarly, if you have the polymer catalyst values, so there these values are given, which is basically beta 2 would be of a value of plus 8.5. So the least square fit with the regression coefficients as given here would be y hat. Now this is y hat, remember that it is not y actual value, and also remember that the error terms would not come now until unless you find out the difference between y and y hat. So here we need to find out the values of the predicted values. Why predicted values? Because we are using the beta hat values. So beta naught value, which you have already found out, is 1566.08. I am just reading till the second place of decimal. Beta 1 is basically, beta 1 hat is basically the value of 7.62, beta 2 hat is basically values of 8.58. So beta naught multiplied by x 1. So what is x 1? You will try to find out. It will be the 21st reading. So beta naught plus beta 1 hat, beta naught hat plus beta 1 hat multiplied by x 1, which is the 21st value, then plus beta 2 hat multiplied by x 2, which is the 21st value. That will give me the y hat value of the 21st value. So y actually for the 21st value minus the y hat for the 21st value would give me the error for the 21st value. Similarly, when I multiply beta naught plus beta 1 hat plus x 1 for the 22nd value plus beta 2 hat into x 2 for the 22nd value, that will give me the y hat for the 22nd value. So y actually for the 22nd value minus y hat for the 22nd value would give me the error for the 22nd value. If I continue doing that, I will find out the errors. If I find out the sum of the errors, it should technically be 0, because that is the assumption. We can find out the errors, the variances of the errors, and do all the calculations as needed. So the first 3 columns in given the table represents the actual observations yi's. So predicted or fitted values of y hats are given, and the residuals are also given. Residuals means the errors. Now if you plot these errors, so the normally plot of the residuals can be done. So obviously they should be normal, because the reason is that we have assumed the x's are normal, y's are normal. So if they are normal, the error term would also have a normal distribution with a 0 mean and a standard deviation which is fixed. Plots of the residuals versus the predicted values of y hats and versus the 2 variables x 1 and x 2 are shown, which is going to come to that. Just as in a design experiment, residual plotting is an integral part of the regression model building. These plots indicate that the variance of the observed viscosity tends to increase with the magnitude of the viscosity, and figures later on will suggest that the variability in the viscosity also increases on the temperature increases. So what I have just discussed, I am going to now show it in a table or the graph plot. Okay, my mistake, there were 16 readings, my mistake, I just mentioned that 20 values. So observations are basically 16 in number. These are the y values which I have said. So basically they start from 2256 to 2328. The predicted values we have found out. So the first predicted value is 2244.5, then the second value is 2352.1, the last value is 2332.1. The residuals errors are found out. So technically, when I mean that if I sum up the errors, it should be 0. Then I find out the studentized residuals. If I find out, then I find out the R values and find out the degrees of freedom, and I can do the calculations accordingly. So the normality plot of the residuals. So normality plot would be, let me mention it. I think I have mentioned it, but I will just repeat it. So what you do is that this will take about 5 minutes. So let me discuss. So consider of the discussion. I am just stepping out of the discussion and coming out to how we do the QQ plots or the quantile plots. Consider you have a distribution, and for the time being, consider it is a normal distribution, which we know. What we know is basically is mean and the variances, and we know all the readings. So for the normal distribution, and that is basically from a population. That means there are infinite sets of observations. So that is kept on one side. On the other side, you have an unknown distribution, which you want to fit and find out whether it is actually equal to the normal distribution. So consider that distribution is the observations are given, that is kept on the other side, on the right hand side. Consider. Now the normal distribution I take, I rank them from the least to the highest and plot it along the x axis. So these are all marked on the x axis theoretically. Now I take the other distribution, unknown distribution, which is on the right hand side, rank them from the least to the highest. When I mean the rank them, and when I rank them, I also have the probabilities, obviously. Now what I do is that I find out the quantile values. So 10% value, 20% value, 30% value, so on and so forth. Now also, and I basically plot them along the y axis. Now draw a 45 degrees line in the graph. Now if the normal distribution quantile, so each step I am going to take for the normal distribution, if the same probability is being covered in the unknown distribution also. So obviously those 1-to-1 correspondence would basically mark the plots along the 45 degrees line theoretically, which means the distribution based on which I am trying to plot these quantile plots and trying to compare that unknown distribution with the normal distribution as they match. Hence we can say the unknown distribution is also normal distribution. So that case, now in the case if the values are above that 45 degrees line or below this 45 degrees line, would give me the idea whether they is skewed on to the left or the right with respect to the normal distribution. So this known distribution or normal distribution, which I said that should be kept on the left, can be in place of normal distribution, can be exponential distribution. So we can compare a known exponential distribution with an unknown distribution, and if it matches, then we can say the unknown distribution is normal. So they can be done, we can do the QQ plots or the quantile plots for the exponential distribution, the gamma distribution, the Poisson distribution, and so on and so forth. So in this case we assume, and rightly so, that the residuals have a normal distribution. So if you plot them, this is the 45 degrees line which we are talking about. So these are the residuals and this is the normality plot. So this can be done on the x axis or the y axis, whatever. I did mention we do it on the x axis, but it can be done on the y axis, and the residuals plots are there. So if you find out these points which are there, they are almost falling. Obviously they are not exact, they are along the 45 degrees line. So we can safely assume that the assumptions of normality holds for x's as well as for the errors. Now if you plot the residual versus the predicted viscosity, so obviously that will give me the errors. Now why I am plotting that? Because if you remember, I have said that the sum of the errors should be 0 in the long run, because that is the expected value of the errors. So here I have the predicted viscosity in centistrokes, predicted y hat, and this is the residuals. So basically I have the residuals being plotted. So this is plus minus plus minus. If I add up the sum of the errors, obviously they in the long run should be 0, because the expected value is 0. These are the way of trying to basically double check the overall concept which I am doing. Two important things which I did mention time and again: the expected value of the error should be 0, may not be exactly 0, but it should be as close as possible to 0. So if I find out the error terms of this plotted would be almost equal to 0 value, where the 0 value would be somewhere here. So this is what it should be. and the error should be basically normally distributed. So, if I basically do the QQ plot, it should be along the 45 degrees line. Now, I do the plot of the residuals versus x1, which is the temperature. Then I do the plot of the residuals with respect to feed rate, which is pound per hour. So, here also you find out. So, this is the average value which I am plotting. These are the deviations. So, in the long run, it should be 0 as it is. It should be also 0. So, this is with respect to x1, this is with respect to x2, and you can do it for y hat and so on. So, I am plotting the errors on the y axis, on the x axis I am taking the predicted values of y, once the x1 values, once the x2 values, and so on and so forth. So, these are basically double checking the assumptions are, which are expected value of the errors and the concept of normality plot. Now, it is basically the regression analysis of 2 to the power 3 factorial design. So, there are 3 factors of the level, each being of level 2, plus minus 0, 1, 1, 2, whatever. A chemical engineer investigating the yield of a process, 3 process variables are of interest. That is why it is 2 to the power 3. That 3 basically means x1, x2, x3, which are temperature, pressure, and catalyst concentration. Each variable can run at a high and a low value. That means what is low and high, 0, 1, 1, 2, whatever. So, if it was basically 3 to the power 3, so that means 3 catalyst values at 3 different levels. Each variable can be run at low and high level, as I mentioned, and the engineer decides to run a 2 to the power 3 design with 4 center points. The design and the resulting yields are shown in the figure 10.65, which are the variables and the values, where we have shown both the natural levels of the design factor and the plus 1 minus 1 coded variable notation, normally implied to root as in the 2 to the power k factorial fractional design concepts. So, the runs are given, the temperatures are given. So, temperature is basically the one of the variables. So, if I go to the, so the pressure is given. So, the pressure in pound per square inch. If I go to the catalyst concentration is given. So, now these variables are coded. So, the codings are done as plus minus of 0 1 0 1 0 2 0 2 and 0 1 and 1 0. So, the variables are given. So, this is at a lower level x1, low level x2, low level x3. So, this is the first one. Let me use a black color. So, it will be easier for me to. So, this one is basically all at low level. This one is that first one is high level, the second two are in low levels, and so on and so forth. And then we have the yields. So, yields is basically the y variable we are trying to find out. So, the temperature is the average value is basically given, the pressure average value is given, the concentration is given, and we basically draw the relationship between the 3 variables in a 3-dimensional figure. So, where along the x axis, y axis and z axis you will basically plot x1, x2 and x3. So, now the equation is of the form y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, because there are 3 variables corresponding to x1, x2, x3 and beta naught for the case where you want to find out that the concept that if you remember y is equal to mx plus c. So, that concept we are trying to put plus epsilon. So, now if I find out the size of x, so obviously the first column would be corresponding to the 1, all the ones, which is corresponding to beta naught. The second column would basically be corresponding to all x's, x1, the third column with respect to x2, fourth column with respect to x3, and y values we have already noted down. So, if you basically have x which would be n cross 4, n is the number of readings. So, that can change, and obviously n has to be more than 4. Why 4? Because beta 1, beta naught, beta 1, beta 2 and beta 3. And similarly, y would be size of n cross 1. So, the 2 to the power 3 is an orthogonal design, and even with the added center runs, it is still orthogonal. Therefore, the 2 to the power 3 can be solved using the simple concept of regression model. We find out x transpose x, which is basically of size 4 cross 4. Then we find out x prime y, which will be size of 4 cross 1, and once we find out, the values of beta naughts are found out, beta hats are found out. Because the design is orthogonal, the x transpose x matrix is a diagonal matrix, the required inverse is also diagonal, and the vector of least square estimates the regression coefficient, and we find out the regression coefficients as beta naught is 51.00, beta 2 is basically 5.62. I am only reading till the second place of decimal. Beta 2 is basically 10. These are hats. Sorry, my mistake. So, I will again repeat. Beta naught is basically 51.00, beta 2 hat is basically 5.62, beta 3 hat is 10.62, and beta 3 is basically hat is basically 1.12. So, these value, and obviously the errors would not be there. We find out the nth plus 1 reading of y, that is y hat suffix n plus 1, find out the errors, which is errors of n plus 1, find out the errors for n plus 2, n plus 3, so on and so forth, add them up, check it there is equal to 0. And you can do the double checking of the normality plot, the QQ plot, the residual plots, check whether the QQ plots are matching with the 45 degree line, check whether the average of the errors are 0, because you are going to plot out the residuals with respect to once with respect to x1, once with respect to x2, once with respect to x3, and then you are trying to plot the QQ plots of the values of the predicted values or y hat values or the error terms with respect to the values of a theoretical normal distribution. As we have made use of on many occasions, the regression coefficients are closely connected to the effect estimates that would basically be closely connected to the effect estimates that would be obtained from the usual analysis of 2 to the power 3 analysis design. For example, the effect of temperature is to refer, and if you find out the temperature values, it can be either plus or minus, because that was one of the variables. So, for all these cases, you can find the difference of the temperatures. So, notice that the regression coefficient of x1, which is with respect to the temperatures, is given by 5.625. So, because we have made them orthogonal, that is the regression coefficient is exactly 1/2 the residual effect. This will always be true for the 2 to the power k design, because there are two levels of, for any factors there are two levels. As noted above, we use this result to produce the regression models and fitted the values and residuals. This example demonstrates that the effect estimate for the 2 to the power k design are the least square values. So, from that we can find out the errors of with respect to the variance of beta naught hat, beta 1 hat, beta 2 hat, beta 3 hat, and they come out to be as given the values. So, the beta naught hat the error is sigma square by 12. So, obviously sigma square is the actual value. If it is estimated, we have to replace by its estimated value, while the beta 1 hat variance, beta 2 hat variance, beta 3 hat variance all come out to be sigma square by 8. Now, these variances, when we find out the square root, this is the standard error, if you remember I did mention that. The relative variance can be found out, and we can basically solve it and basically have a nice idea how the regression models can be utilized for this type of ANOVA models. And obviously, you will again at the end of the day, you will have basically the number of readings, the sum of the squares, the degrees of freedom, the f values, and whether they are matching with the PP to what level degrees of freedom, what levels of confidence you are able to predict. So, that the ultimate table is basically the ANOVA table that will be can utilize here also. So, with this I will end the 37th lecture and continue the discussion of the last 3 lectures with respect to the more further models of regression and ANOVA models, and a few remaining topics which are there in this TQM2 course. Thank you very much and have a nice day.